So I hope you've seen this document already. Okay, I've talked about this. It's been on Moodle for the last week. One of the big things you'll see here is that I added, and I didn't do this last year, I did this starting this year, is multiple choice questions. I think that'd be very useful for those of you that struggle a little bit with multiple choice. And there's a good amount of them in each section. So just look for MC in each of these and you'll find the multiple choice questions listed for each chapter. Aside from that, the other questions listed here are comprised of both short answer and math problems. The test itself is pretty much the same format as all of your tests. If you've recognized by now, I usually give you guys like between 8 and 10 multiple choice to start, a couple short answer, a couple math. And it's usually around 40, 30, 30 as far as percentages. It's about the same here. Instead of making problems worth 2 points though, since it's a midterm, 2 points is a lot, right? If you get one wrong. So I give 40 problems. It doesn't make this exam undoable. It makes it actually, most students finish easily. But you have 40 multiple choice worth 1 point each on the midterm, okay? Think about each test. You've had 6 tests so far with between 8 and 10 multiple choice. You've had about 60 multiple choice this year. I'm giving you 40. So I'm obviously not going to be able to cover every single thing in the multiple choice. So some of that stuff that's not covered there is covered in short answer. There's almost no chance that a topic isn't going to appear in the midterm. Anything that we've covered this year will appear in some facet or another. The only thing that you can omit are the 2 questions in the last part. So if you take a look at the setup here, you'll see for the last part of the test, you're given 8 math problems. You're choosing 6. So you can omit 2 of them, which kind of tells you if you want to, you can start to pick and choose. If there's a category you really struggle with mathematically and you don't want to spend too much time reviewing, you can already assume ahead of time you're going to omit that topic. All right, the most you'll see from any topic would be 2 questions because there's only 8 questions and we only cover like 6 main topics. All right, so there might be 2 for one topic, but that's the most. The formulas are listed by group. Obviously here, recognize that this is X and Y, just like on the formula sheet. I think that's pretty much it for this review guide. And then at the end, I just put some stuff that you should be looking at. So you should definitely look into your problem sets. Okay, 1 through 6 are listed. 6 is not listed yet. I have to put that one up. So I'll put problem set 6 up still. I was giving 1 or 2 people a little more time that were out for the test. The mathematical questions, all the solutions to all the math problems on the test are on Moodle. They're under documents and handouts on Moodle. If you don't know where that is already. Okay, documents and handouts. Old homework assignments to look at for sure. When you're looking at example problems, write yourself a little note here. In the example problems, I usually go into like a really complicated problem, usually at the end of each section. Since this is a midterm, there's going to be a bit of a broader range of topics because you're covering everything. So they're not going to be as difficult in the sense of it being like the most difficult problem from the notes. So if there's a problem that involves like, we did one with work, kinetic energy, with friction, all that kind of stuff all together, that'll most likely not be a big problem on there. So if you're really studying a lot of your note examples, look at mainly the beginning ones, maybe not the toughest of them if you want to drop one off. If you find that you totally get everything, you want to challenge yourself, look at those problems for sure. But if you're trying to optimize your studying time, that's how I would approach it. Only the math parts, that's what I put here. So tests 1 through 6, all of the mathematical questions are on there. The short answer and the multiple choice are not. But again, multiple choice right here, right here, right here in your textbook, those are all multiple choice questions. Okay? And a lot of conceptual questions appear in these. So for those of you that have trouble with even the short answer type questions you'll find in these example problems from your text. If you do decide to practice these problems, I will happily give you credit for homework, but it is not required. I cannot force you to study for the midterm. I really hope you all do. But to be completely honest, for those of you that have had 95s all quarter or all semester, you probably won't have to do much studying. So I'm not going to make it a requirement that everybody has to do all these problems because then suddenly you're getting penalized when you really know everything from there already. So depending on who you are, you might do more or less. So if you do a lot of these problems and you want to get a homework credit for it, just submit it to Google Drive and I'll find it there and I'll give you credit. Okay? And then finally at the end, make sure to look at your labs. I have one of your labs still. Okay, that's the one I'm working on. I'm going to try to get it for you hopefully so that if I see you later this week, I can get it back to you as you're leaving for like your math exam on Friday. So I'll try to get it to you on the way out the door. I'm trying to grade it, but it's just very difficult to catch up. But you have all of your labs except for the last one. Questions? Okay, yeah. Yeah, so if you want to get a homework credit for this assignment, definitely submit it before the midterm at the latest. And after the midterm, I'm not going to count it. Okay, but yeah, before next Wednesday is fine. And I'm going to look at your Google Drive folder, but if you want to even shoot me an email, hey, I submitted the file, just so you know, especially if it's last minute, like Wednesday morning or something. But if you submit it over the next couple of days, I'll see it appear. I always see the notifications. No, it's not for I'm not going to check them at all. Honestly, I'm not even going to look at them. I'm going to look and see, all right, looks like they did a lot of work. I'll give them a 5 out of 5 for homework. Or this student did like a ton of work. I'll give them 2 homework credits. You know what I mean? So it'll be individually based on how much work you do from that. Just because I want to reward you for some of the work you do, even though it doesn't always show up on tests. Sometimes it's hard to, on a formal assessment to see that. So on the next page, you'll see that these are just sample problems for mathematical section. So feel free to practice these. These are good samples, and you'll notice there's 9 of them here. So this is very similar to what you're going to see on the actual midterm in the sense of breakdown. So you'll definitely have problems with one-dimensional motion, maybe 1, maybe 2. You'll definitely have a vector problem and a projectile motion. I'm telling you now. You'll have one of each of these for sure. You'll absolutely have a forces problem. You'll have a work and energy problem. Within work and energy, we also covered the work kinetic energy theorem. So we have the work kinetic energy theorem in here. We've got conservation of energy. So there's several types of problems you could expect for this section here. And then finally, momentum at the very end. There's one example, which is the one we just covered on the test. Okay? It's very similar to literally what you did on the previous test. So this is stuff you can practice. I'm not going to sit here and do this for you right now. But how about questions on things that you want to study? Maybe questions on either like topics or specifically saying like, there's a question I've tried from this packet already and I want to go over it because I'm struggling with it because of this or this. What's up? Vectors? Okay. So I spent a long time in the other class going over a long, lengthy math example of vectors. So I'm going to go over the intro and the theories behind it, and then maybe want to look at the other video, and it's already on Moodle, and it goes through it's like a 15-minute example on vectors, breaking it all down to components every time along the way. I'll show the introductory part of it, and then maybe we'll go on to something else for that reason. Okay? But I've spelled it all out. I went through it all very slowly with the class. So generally, though, we do need to know about vectors, and this is what I want to cover, because this is stuff that will show up in the mathematical portion or in the short answer or multiple choice. Vectors in general are things that have, what? 2 components. What do we call them? 2 things involve a vector. What are the 2 things that make up a vector? Magnitude and direction. Magnitude and direction. It's important to recognize that there's the direction because the direction is what gives us the x and y components of the magnitude. Remember, when you have a vector, it's got the y component and it has the x component. So let's draw a vector on the diagram. So we'll start with, say, vector A. And the length of it is, say, 7 meters. And vector A is drawn at an angle of 23 degrees. Now, if that's the case, and look at specifically this example, please. Which way does this vector move? And give me directionals. Give me directionals. Which way is this vector pointed? Is it pointed northeast, northwest, southeast, or southwest? You've got 4 options. It's not north, it's not south, it's not east, it's not west. We know that, right? Right off the bat. Andrew, what do you think? Northeast. And the reason we know that is because we naturally go this way and we go up and say, well, this point here, God bless you, is north of the east line. It's 23 degrees north of east. Remember how I spelled that out and said north of east? So it's 23 degrees above the east line. Well, this is the east line right here. So 23 degrees north of east. This being east. If it was east-north, it would be 23 degrees east of the north line. This is the north line right here, or the y-axis. East of north would be this angle. But we're saying northeast. Very good. Traditionally, it's written as northeast, northwest, southeast, or southwest, because the angle is usually given with respect to the x-axis. Now, if a person walks that, let's make it miles, just because it will say walk. If a person walks that distance of 7 miles, and they are able to cut across Central Park in doing so, well, that'd be 7 miles. Well, Central Park is 6 around, so that's too long. Whatever body of land this is. And then suddenly, that body of land is no longer passable. And the person has to take this route instead, the longer route. What would those values be? If the person had to take a route that followed this following path, from here to here and then up, what would this value and this value be? Simpler than you think. Don't overthink it. What would this value be right here first, right? The x value. And what would this value be here? Right, what's the y value? Mike? They could be, but not necessarily equal. I'm asking, like, how would you calculate those values? What would you use? What expression?
X plus y? Or, sorry, what am I thinking of?
The distance would be x plus y. I'd agree with that, whereas the displacement is just 7. But I'm asking you, what is x and what is y in this case? How would I calculate the length of x and the length of y? If I want to use this here, I'm going to write the word displacement, or I'll put the vector r for now to explain the difference there. What's x and what's y? How do you find your components?
Would x be cosine of theta and y be sine theta?
Not just cosine theta. What else? You're forgetting. I can't just write, like, for example, this is not just cosine 23. Jack?
I was about to say, cosine 23 divided by...
Don't try and solve it.
No.
Try to memorize this one, guys, honestly. Marilyn?
Is it times magnitude?
Times the magnitude. So it's always magnitude times cosine of the angle. And then the y direction, what's the only difference? The sine of the angle. So remember, please, that whenever you're breaking something up into its components, you use the sine and the cosine to get the y and the x. I remembered alphabetically that x is cosine and y is sine. So this person can take the 7-mile route, or he or she could take the 7 cosine 23 route, and then add to that 7 sine 23. In this example, would the person's distance or displacement be larger? Distance or displacement, which would be larger? The distance. Because the distance is accounting for the path traveled. It's this full length plus this full length. And you know that if you sum together the two sides of any triangle, it must be greater than the third. That's one of your laws from geometry. The sum of any given sides of a triangle, two of them have to be bigger than the third, always. So even though I don't know what this x is here and what the y value is here, right, I'm unsure. I don't know what x is yet. I got to calculate it. You could do that. What is the y value? I don't know yet. But I know that if I add these two together, it's got to be greater than this. So the distance traveled is always greater than or equal to the displacement. That was one of our theories that we used. Okay, now, how does this tie into the mathematical portion of vectors? Well, if you have several vectors attached to one another and you want to find the overall motion of the object, and I did this in the other class, so take a look further at that video and you'll see that I also attached another vector here, and then our goal was to find the overall displacement from beginning to end, that dash line. Okay, that was what we did with the other class, and I broke this into components. So we had a number here, we got a number here. This was a given value, say like 3 miles, and then we found the x and y and put it all back together. So for a mathematical type problem on vectors, just take a look at the other video from the other class. Okay, instead of doing it twice. It doesn't make sense to do that because you guys can watch that one. What else? What else after vectors? Yeah, this is the general conceptual and multiple choice type stuff that you would get is what I'm showing you here, obviously. The math part is the other stuff in the other video. What are the topics you struggle with? What do we have? We've got one-dimensional motion, we got projectile motion, we got forces, we have work and energy, and we have momentum. We have all those topics right there. Which was the one that you struggled with, you think? I can't read your minds, right? So you got to help me out. Here, Martha, go ahead. A what? Okay, work and energy. Good example. So let's think, what if we want to look at a problem where we're involving either work and kinetic energy theorem or conservation of energy? Let's start by writing down those things. So first, if we want to calculate the work done by an object, we know the formula is FD cosine theta, which means that work can't be done if there's no distance traveled. That's the first part. So I can push on this table as much as I want. Look, I'm pushing, right? But if it's not moving and there's no distance traveled, I'm not doing any work on it. And the reason for that is because the work and kinetic energy are related also, right? The work done on an object is equal to the change in that object's kinetic energy. So if you do work, therefore you're moving it, therefore you're giving it kinetic energy. Kinetic energy is the energy of motion. So all this stuff that we've been learning always ties back. So these are the first two formulas. And then finally, we know conservation tells us this. That the energy in a system before was the energy in a system after. And what does before and after mean? It means before some sort of motion it's undergone. So maybe it's an object that is starting at rest and it's compressed in a spring like a pinball. And then you release the little pinball handle and then that ball starts to fly, right? As it goes, I should make that a simple project maybe. Roller coasters are so lengthy. What about a pinball machine? Think about it. Elastic energy, it then has to shoot up, gaining potential energy while moving, gaining kinetic energy. It hits a bumper, right? When it hits the bumper, it gets launched, right? Because there's a spring in that bumper. There's elastic energy in the bumper. You can determine how much by calculating the velocity of the ball after it hits the bumper. A pinball machine it's actually a great example of conservation of mechanical energy. You're constantly converting, because how is the pinball machine angled? Isn't it tilted down? So as it moves down, what is it losing? As it moves down in height, what does it lose? What kind of energy? Potential energy. When it hits the springs and gets launched, it's using up elastic energy. When you release, it uses elastic energy. When you release the little whatever, what is that called? The thing you pull back. Is there a word for it besides spring? Okay, well, whatever that thing is that you shoot, the knob, yeah, to release the actual pinball. And then kinetic energy is obviously changing as well, because as the pinball moves around, what changes? Its velocity. So kinetic energy is constantly changing. That's a great example of conservation of energy. Maybe I'll put that on this. So let's take a look at an example mathematically of something for this. Let's say you could write this down if you want. Some of you like to type or write it down. I'll give you a quick scenario, or you can just list your givens as I go through the problem. So let's say that an applied force of 17 newtons acts on an object at an angle of 22 degrees. An applied force of 17 newtons acts on an object at an angle of 22 degrees above the direction of motion. Above the direction of motion. If the surface it's on is frictionless, this allows us to make the problem a little bit easier. We don't have to subtract FF. If the surface it's on is frictionless, determine how far it would move if its mass were 2 kilograms. Determine how far it will move if its mass were 2 kilograms and its velocity went from 3 meters per second, or changed from 3 meters per second to 8 meters per second. So we're using, if we look at this problem, well, I won't jump to the conclusion yet. Here's what was listed, okay? This is what was given in this problem. Let's think about it. Let's go through each part. It said to start, a force of 17 newtons was applied, that's F, at an angle of 22 above the horizontal, theta. If the mass of it said, how far will it travel if the mass of the object is 2 kilograms, that's M. And it travels, and it changes velocity from 3 meters per second to 8. Well, 3 is initial, and 8 is final. So the givens should be something that you're getting better at. As the year progresses, a lot of you are getting, God bless you, much better on the math portions of the test because you're getting better at doing exactly this, which is recognizing what's given in the problem, breaking down the problem and analyzing it that way. The next part is the harder part for the midterm. Why is this next part going to be tough? Why is this next part that you have to do in this problem tougher than any of the tests you've done? What have you been lucky about for each test, whereas the midterm you're not kind of lucky about this, unfortunately?
You know what the formulas for that test?
Yeah, exactly right. Each test you've had how many formulas, really? 3, 4, maybe 5 sometimes, but only a limited amount, correct? The midterm, how many formulas do you have? All of the formulas you've used so far. So I look at a problem like this and I ask myself, well, it involves forces, it involves velocity, so it could be just a force problem. But it also, since it involves velocity, it could be an energy problem. Because it involves forces, it could be a work problem. Because it involves velocity, it could be kinetic energy. And I start to think in my mind, which of those make sense together? Does force make sense with work? Yeah, it does. But am I going to be able to find work alone? I don't have the work, I don't have the distance, that's not enough. But I have something with velocity and force. Where's velocity and force kind of used together? Only one instance all year, really, where velocity and force are really utilized together. Well, not one, two. There are two instances where velocity and force are used together. What is that? Any idea?
F equals to ma.
You can do F equals ma, very good, because A is really acceleration. You would need time, though, to get acceleration, right?
Yeah.
So you have the change in velocity. You would need the time to get acceleration and then use F equals ma. So that's on the right track that F and A are related for sure. But there's somewhere else also that actually force and velocity are specifically related to each other. I'm giving you a hint because, the question was just posed, Martha asked about energy, right? Work and energy. So where do you think it's going to be? It's going to fall from one of those. So out of the equations or the ones I just listed, which of the three you think would work? I listed W equals FT cosine theta, W equals delta KE, and then MEI equals MEF. But what's missing in that formula? D, N, W. Do you have W here? So that's on the right track, that it's going to be like that. W equals delta KE. W is based on what? FD cos theta. You got F, you got theta, but you don't have D, right? So you know all those. Delta KE, what is KE based on? Two things. Come on, KE, what is it based on? Two things. What parameters? What variables? Two things. Mass and velocity. That should be like instantaneous at this point. Mass and velocity. And those are both given. And since it's a change in kinetic energy, you would need a change in velocity. It happens to be given. Okay, so that's how you have to approach these problems. It's not as easy as the earlier test in the year because you have a wider selection of formulas to choose from. But at the same time, when you list all of your possible givens, right, there's only some that will work. Maybe you could have an option of two sometimes, and either way is fine if you could have an option of two. But for most of these problems, only one of them will sufficiently cover all the variables except for the one you're looking for. So here we're looking for D. So I would start with this formula first. Replace work with this. So inherently, Tiana, we were using that formula, we're replacing W with FD cosine theta. But we also have to replace delta KE with KE final minus KE initial. Oh, oops. KE final minus KE initial. So F is the force applied, D is the distance, theta is the angle. This is 1/2 mvf squared minus 1/2 mvi squared. The only thing that's unknown is D. That's it. All right, there's your only unknown, D. So I'm not really going to go through the process of solving this at this point. You should be able to at least plug in and understand how to get the solution. Every other given is shown here above. Literally plug in for every other variable in this formula and solve for D. Yes?
So I just memorizing how to formulas. Could you just go straight from the first equation and then kind of just know that you have to go to...
Yeah, for sure. From W to delta KE down to the blue one?
Yeah.
Yeah, absolutely. That happened several times. Even with the delta P equals FT, the in momentum impulse theory, instead of PF minus PI, you could just go right to MVF minus MVI. Yep. How would this problem change, okay? How would this problem change if instead of a force being applied, this object were compressed in a spring, a horizontal spring still though. So imagine a spring that's attached to the wall, like a slinky or some sort of a spring. You compress it and you let go and the object starts sliding. It's only on a horizontal surface. So now there's a spring involved instead of a force for a distance at an angle. Forget the force, distance, angle, and now there's a spring involved. How does it change? Do you still use work kinetic energy theorem? I'm giving you a hint by saying, do you still use it? Let me think. I'm no longer giving you force, no longer giving you theta, no longer asking for distance. Instead, the problem now involves a spring. Would this still be included? No, it wouldn't. Come on, people. This would not. If it's no longer there, you don't include it. So if this problem involved a spring now, and it started, right? Let's say it started from rest, and it was a spring involved, you would now have to consider the fact that you've got this scenario. Here's the object at rest, compressed in the spring. So what kind of energy does it have right now? Before it's released, what kind of energy do we call that? Potential elastic, or just potential, or just elastic. We're making sure, though, it's not the gravitational, though. So potential energy elastic in the beginning. It's not moving at all, literally. It's on the ground, it's on a surface, it's on a fixed surface. And then the spring, a little pin is pulled, and the spring launches it, like a pinball machine, right? This is literally a pinball machine right here. You let go of that knob, and it gets launched off. What are you giving the ball by launching it? What kind of energy are you giving it? Kinetic energy. That would be the setup. And where does this come from? This comes from the following. MEI equals MEF. And a lot of you by now have started to realize that you don't have to list MEI equals MEF every time. Just list the energy to start, list the energy at the end, and go ahead and calculate. What will not drop off in this instance that usually does drop off with energy? When we do energy problems, something seems to drop off a lot. Something that we utilize a lot. Always we're like, oh, that cancels out. Oh, that cancels out. Very nice. Yeah. Mass. Mass usually cancels. Why won't it cancel in this circumstance? Why won't mass cancel for this equation? What does my next line look like? That's the easy answer, right? What should the next line read? Travers, what do you got? Yeah. And the rest we know K, but if the key here is the PE. There's no mass involved when you're finding the potential energy in a spring that is compressed or extended. It's a function of the spring itself, not the mass. What does K stand for? What does K stand for? Yeah, good. What does that mean, though? Do you want to elaborate further? Go ahead. A larger K versus a smaller K. What can you tell me about that? L would be length, right? And the X is the change in length. Mike? The strength, not just the constant. The constant is the name of it, but it's the strength, really. A higher K means it takes more strength to compress the spring. A smaller K would be a K that's like in your pen. The spring you pop out of your pen, that little weak one, that's a small K value. How would this problem change? See what I'm doing right now? Do you notice what I'm doing on purpose? I'm literally taking one problem and just slightly altering the scenario to show you that the problem suddenly is a little bit similar, but you need to change up your formulas, right? How would this change if this object were no longer just compressed, but it were compressed on top of, like, say, a surface, and then eventually it falls down here? How does it change now? And we're going to call this, sorry, I should give you some sort of a reference. That's potential energy equals 0. There's your reference line. Remember we drew this? You always have to draw a PE 0 line. So we're going to call that ground level. So now it starts here. Compressed. It's at rest. Pull the pin. It gets launched. It moves, it moves, it moves. It falls, it falls, it falls. It crashes into the ground. End of the problem. Beginning, end. What happens? What's the difference? Come on, compensate for it. Think about it. What's the change I just made? I've now given the object what? Very good. I've given it height to start. It doesn't start on the ground anymore. Remember earlier, this was like the ground, wasn't it? We didn't have this little cliff, this little drop off. But now it starts from an elevated position. So you're giving it potential energy. Not only does it have potential elastic, but how would you account for that? You would have potential energy due to height in the beginning, which is mg yi. And nothing else has changed. Look at that. It's got height. It's got elastic energy in the beginning. And at the end, when it hits the ground, it has no more height, no more elastic, but it does have motion energy, which is kinetic energy. So the kinetic doesn't change. The potential elastic is still there for sure. The height, though, is added to the problem. Okay? There are so many ways I could vary this. What if this object landed on a trampoline? Isn't that a spring, the trampoline? Now you got a spring at the end of the problem. And the problem now might say, all right, if the velocity when it's about to hit the trampoline is 10, well now you know your V, you're not solving for it anymore maybe. Determine how far the trampoline gets extended. Like, think about a trampoline, they're like this far above the ground, right? So if you land on the trampoline and you stretch it more than about a meter, what would happen? What would you hit? You hit the ground, right? So maybe you have to consider like, all right, you can figure this out mathematically, and this is not a joke at all. If you were to, and I want you to try this, so please don't just try this. Maybe figure it out mathematically, then try it. But if you just jump off part of your roof onto a trampoline, you could give it too much energy that you would either A, tear through the, you probably wouldn't tear through the trampoline, but you could stretch it so much that you might hit the ground and actually do damage to your legs. You wouldn't actually get hurt from the bounce afterward, but you could go stretch so far that the delta X value, the stretch of the trampoline, is more than the height of the trampoline, and therefore you bottom out to the ground. You could also just get lodged and hurt yourself separately there too. But what I'm saying is that if I suddenly place a trampoline at the bottom, now at the end of the problem, we no longer have just kinetic, we have kinetic and potential elastic, because now it's stretching the actual thing. So the problem can vary depending upon the scenario of the setup. Okay? Others. What I literally just went over with you is like if you can understand that and work through a problem like that and continue to understand as you change little bits, more changes, that's really what work energy is all about. That's the entire chapter on work energy kind of summarized there in one big problem. Okay, because we also talked about the work kinetic energy theorem to start that problem.
Oh, give us a
Yeah, Mark, what's up?
Give us a formula she has midterm.
Mm-hmm. Same one you got all year. Literally the same highlighted one you get. Yeah.
This is a weird question, but like I remember social society and more like other like worksheets and like quadratic formulas and all that. They weren't like any like that.
Not outright, but you have to know how to use them.
Yeah.
So that's a good question. You guys hearing this? So the question is, the stuff like trig and the quadratic worksheet and dimensional analysis and conversion, are there going to be questions on that? There will be no direct questions. It's not going to be like convert 24 inches per second to miles per hour. Absolutely not. But in problems, you will have to do conversions. So if a problem is given in grams, you need to know to put in kilograms. If a problem is given in kilometers, put it back to meters. You know what I mean? So inherently, it will be embedded in the test. So the quadratic formula may have to be used on a projectile motion problem because you have t and t squared, right? And so if you have a quadratic, you need to find your x-intercepts. You know this from your math class. X-intercepts, the zeros of the function, right? All that kind of stuff. So it will be utilized, but not directly asked. Okay? Yeah. Yeah. With what? Mu? Okay. I hear what you said. Yeah, so mu Fn. All right, so these problems are forces, right? These are forces problems. So if we're looking at forces here, we might have mu, which is the coefficient of friction. We might have an object that's moving or stationary. For example, let's say an object is stationary, and the question says, if the coefficient of static friction between the object and the surface is equal to 0.2, and the mass of the object is 5 kilograms, and the mass of the object is 5 kilograms, determine the necessary force, determine the necessary force that would be needed to set it in motion. Again, an object is stationary on a surface with a mu value of 0.2 between the surface and the object. If the object's mass is 5 kilograms, determine the necessary force needed to set it in motion. And all year we've been calling that FP, for push or pull. Free body diagram, go. Free body diagram, come on, quick, let's go. Help me out. Free body diagram. What's happening? Martha, give me something. Very good. What else? You got more? Doesn't matter. Either direction. You pick.
It's going
Left? And then what's right? Yeah. If FF goes left, FP goes right. But if FP went right, if FP went left, FF would go. You know what I mean, right? Okay, again, if you're pushing it one way, which way does friction act? The other way. Friction opposes motion. Friction opposes motion. So in this setup, this is what we have. And all this is, remember, all this is the idea that we have right now, it's not moving. It's not moving. We want to get it to just move. To just move, right? If it's not moving, we know that FP is equal to FF because it's not moving. Well, where does that come from? That comes from the sum of the forces in the X equals MA. Sum of the forces in the X tells me FP is right, FF is left, and there's no acceleration, so that drops off. Remember what we did already in class. We did this many times, and a lot of you are good at this. All you got to do is list the arrows. FP is right, call it positive. FF is left, call it negative. It's not moving yet. We're trying to just get it to move. So we want this to just be greater than 0. Okay, we want it to just start to move. So we can actually write a greater than symbol instead of an equal to if you want to. It doesn't matter really. Okay, but the problem we're going to run into is this. If I want to know what the force needed is, I need to know what friction is. And friction is mu Fn. I've got mu, but I don't have Fn. Fn is the? Why? Go ahead.
Because it's not moving, so I guess they're the same force.
Yeah. If it's not moving vertically, it's in a state of vertical equilibrium. Fn, give me like 10 seconds. Fn equals Fg, so Fn is simply the mass times gravity, mg. Okay, but the vertical, again, the vertical direction is also in a state of equilibrium. So tomorrow, we will continue to review. Tonight, we need to look at 6-4 power. If you want to practice the homework, you can. I'm not going to collect it, but if you're going to practice the homework, it's good. We'll go over that tomorrow. And also tomorrow, we'll spend like 10 minutes just quickly going through the roller coaster. If you're already submitted it, but I want to see, just show others what yours end up looking like. Okay? We're trying to get it done. Those groups that are still late, are still working, I'm trying to get it done before tomorrow. And you see if something actually like just show the class. Okay, sorry.
After this one. So what I guess over time,
When did you spend that?
I don't know. I don't know.
Matt, your group member?
He's the one who was supposed to.
I got the math today because it was Matt, right?
Yeah.
Yeah, I got the math 5th period, so that was late for sure. That's a full day late.
Like how many points?
10%, full day.
10%?
10% of your grade.
Of the entire grade or just the math?
Well, the math will be 10% off. The video, if the video is late, that'll be 10% off.
Well, the
but if
video
the
was
written is on
submitted-
time, you're good.
Okay.
The written
The
part.
video was submitted yesterday though.
When?
At like 6.
Yeah, that's late. It's PM?
Yeah.
Yeah, it's way
so
too
that's
late.
like 10%.
10%.
Off.
Yeah.
So that's 20% off already?
No, it doesn't work like that. 10% of each of those things.
Oh.
So like if the math part was worth 5 points, I have a breakdown for it, then it means you guys lose an half point off the bat on the math part.
Okay.
If the video is worth 10, there's 1 point off the video part. But the written part, if that's not late, you get full credit for that one.
Okay.
Okay? Yep.